Hey everyone, and welcome. Today, we're going to pull back the curtain on something that secretly powers pretty much every single piece of software you use: data structures. But don't worry, we're not going to be writing code. Instead, we're going to figure it all out by organizing a library right from scratch.
I know, that's a pretty bold statement, right? But just think about it for a second. Imagine a library where every book ever written is just dumped into one giant chaotic pile on the floor. I mean, all the knowledge in the world is right there in that room, but it's totally useless because you can't find a single thing. Well, raw, unorganized data, it's exactly the same. It's not information, it's just noise.
And that is the big question. How do we bring order to all that chaos? Well, for our explainer today, we are going to become librarians. Our job is to take that mountain of books and build systems, these data structures, that let us find, add, and even remove information as efficiently as possible.
All right, so first things first, what's the most obvious, most straightforward way to do this? Well, we could just build one single, massive, continuous bookshelf, and then we give every single slot on that shelf its own number, or what programmers call an index. And just like that, we've created our very first and maybe most fundamental data structure, the array.
So an array has two really important traits. First, it is blazing fast for finding stuff. If you know you want the book in slot number 72, boom, you can go right there, no searching needed. But, and this is a big but, it has a fixed size. If you build a shelf for 100 books and then you get book number 101, you're kind of out of luck. You literally have to build a brand new, bigger shelf and move every single book over.
And yeah, that whole fixed size problem, that's a big deal. Let's say our library is a huge hit and we're getting new books all the time. We need a system that can grow and shrink without all that hassle. So let's try something a little more clever, a little more dynamic. Instead of one giant shelf, we'll set up a kind of treasure hunt. And this is our next data structure, the linked list. So, how does this treasure hunt actually work? It's pretty cool. Each book can be stored absolutely anywhere in the library. But inside the cover of every single book, there's a little clue. A pointer is the technical term, and it's just a note that tells you the exact location of the next book in this series. So if you want to add a new book, you just stick it anywhere you want, and you just update the little pointer notes in the books on either side. It's incredibly flexible.
And right here, this is the fundamental trade-off. If you need to grab any random book off the shelf, the array is the undisputed champion. It's super fast. But with the linked list, you have to start at book number 1 and follow every single clue to get to, say, book number 72. On the flip side, when it's time to add or remove a book, the array is a total nightmare. The linked list, it's a piece of cake. So you're always choosing between speed of access and flexibility.
Okay, so we have our general shelving systems figured out. But, libraries have really specific jobs to do, right? Like managing the book return cart or the long line at the checkout counter. Well, our digital library needs specialized tools for these kinds of jobs too. So let's take a look at stacks, queues, and a really clever trick called hashing.
A stack works exactly like that book return cart. The last book you toss on top of the pile is the first one someone takes off to reshelve. We call this last in, first out, or LIFO, and it's exactly how the undo button on your computer works. Now, a queue is the complete opposite. It's the checkout line. First in, first out, or FIFO. This is perfect for anything that has to be handled in the order it was received, like sending jobs to a printer or buffering a video you're streaming.
But what if we could find any book instantly without having to search at all? Well, that's the magic of hashing. Think of it like a magic card catalog. You give it a book title, it runs that title through a special calculation, a hash function, and it instantly spits out the exact shelf and slot number. No searching required. The only tricky part, sometimes two different titles might point to the exact same slot. That's called a collision, and programmers have all sorts of clever ways to organize the books within that one slot.
Now, even if we don't have a magic catalog, we can still be incredibly fast as long as our bookshelf, our array, is sorted, say, alphabetically. Instead of checking every single book one by one, we can use what's called a binary search. You don't start at the A section. No, you go straight to the middle of the library. Is the book you want in the first half or the second half? Whichever it is, you can now completely ignore the other half. You just got rid of half the library in one step. You just repeat that process, cutting the problem in half over and over until you land right on the book you need. It is unbelievably efficient. Okay, so far, all our data has been in a pretty simple line, right? One book after another. But a lot of the time, the most important information isn't the item itself, but how it relates to other items. For that, we need structures that can map out these complex connections, and that's where trees and graphs come in.
So a tree represents a very strict hierarchy, just like the Dewey Decimal System. Every item has exactly one parent, leading all the way up to a single root at the top. The file system on your computer? That's a tree. A graph, on the other hand, is a total free-for-all network. Think about academic papers. One paper can cite 10 others, and it can be cited by 20 more. Anything can connect to anything. Social networks, airline routes, Google Maps, these are all massive, complex graphs.
So we've looked at simple bookshelves, treasure hunts, checkout lines, magic card catalogs, strict hierarchies, and giant connected webs. After going through all of that, which one is the absolute best? Well, that brings us to what might be the single most important lesson of this entire explainer. There isn't one.
Here is the key takeaway. Real efficiency in software isn't about finding one single magic bullet solution. It's about looking at the problem you have and matching the right tool to that specific job. Is your data rarely going to change? An array is going to be your best friend. Are you constantly adding and deleting things right from the middle of a huge list? You're going to want a linked list. It's always about the trade-offs.
And this really is the foundation of our entire modern world. Your social media feed, your GPS navigating you through the city, your computer's operating system, they're all just incredibly complex libraries, all built from these simple parts we just talked about. The logic is exactly the same. So now that you can see the blueprint, it kind of makes you wonder, what will you organize?